Hello, all. Hope you are doing well. So, we are continuing with the acid, bases, and salts lecture 8. So, we are going to discuss the last commercial salt that I'm going to discuss in this plaster of Paris. It's also called as POP. So, plaster of Paris is written in this form calcium sulfate hemihydrate. Now, this half molecule never exists. It's something that we write on pen and paper theoretically. The actual molecule is 2 units of calcium sulfate loosely bonded to one water molecule. This is the actual formula of POP, but we simplify it to this. That is okay. So, now moving to the preparation. How do we prepare plaster of Paris? We do it from gypsum. So, gypsum is the raw material. So, gypsum is calcium sulfate dihydrate. So when we heat it at not just any temperature, but it has to be 100 degrees Celsius or 373 Kelvin. So we need to maintain the temperature. It shouldn't be less than this or more than this because it can hinder the reaction. So we are going to use calcium sulfate, gypsum, and when we heat it, we will get calcium sulfate hemihydrate along with 3 by 2 molecules of water. Now, if you want to write this way, where you're getting the actual formula, here. So, this is plaster of Paris, POP. So, both are correct. Temperature is 100 degrees Celsius. Now, this should be controlled carefully. Otherwise, what we can get is like if we have a gypsum, if the temperature goes beyond 100 degrees Celsius, then we will get anhydrous calcium sulfate along with 2 molecules of water. So, this is what we call as dead burnt plaster. Or anhydrous, that means without water, calcium sulfate. So this is you can say we don't it's not like it's going to change into some black substance, something dead burnt plaster. They all are going to be white color substance only. Gypsum is also white, so this POP is also white, and even the anhydrous calcium sulfate that we will get, that will be also white, just that it will not have any POP like properties. POP, if we try to put water in it, so it sets into hard substance, that property will be totally gone if we try to heat more than 100 degrees Celsius. That's why controlled reaction is required over here. Then we go to the properties of plaster of Paris. So the very first property is it's very much odorless, it's white in color. Then at room temperature, plaster of Paris absorbs water and large amount of heat is released. So that means adding water in POP is very much exothermic in nature. Then when we are going to mix water and POP, so it forms a plastic mass and quickly sets into hard porous mass within minutes, right? It actually becomes hard. That's why for any kind of science models, we use pop, we use pop for various uses, for making molds, statues, right, for making chalks, fireproofing material. So many uses are there. So now this entire thing, like, is what we call as a setting process. So it turns into, this is what we call as a setting process when we add water, and it actually becomes hard after some time. And during setting process, we can say there is slight expansion in volume which occurs. So it is due to this property, because it can expand, it can fill any kind of mold, and it can give sharp impressions. So again, if you add pop, calcium sulfate hemihydrate, and into water, so what you will get, you will get gypsum again. And gypsum is hard mass over there, right? So we can actually, plaster of Paris can be used in casting for decorative materials, for fireproofing, which I told you, and it can be used for immobilizing the affected parts, specifically in bone fracture or any kind of strain. Then it's used to fill gaps on any kind of walls, roofs. So many uses are there, for making toys, right? So then we go to different kind of substances. These definitions are very much important. So we'll start from efflorescence. So efflorescence. So efflorescent substances or phenomenon, or we can just write efflorescent substances. Obviously, these substances, when we are going to define, so they are going to define the process also. So these are chemicals which have water associated with its molecules, and which, when exposed to air, loses this water through evaporation. Or we can even say loses its water of crystallization. So example that we can take is drying of cement, one example, right? So we have blue vitriol, even that can lose its water of crystallization. We have washing soda, Na2CO3 dot 10H2O. So if we try to heat it, so maximum it can lose 9 molecules of water. So this is the maximum. So even you could say Na2CO3, most of the hydrated salts are efflorescent. So they have water associated, and they will lose water of crystallization when exposed to dry air. So you can say the air that we are talking about can be dry, cannot be, depending. So it depends. If it's too much dry air, then more number of water of crystallization can be released. If it is less dry air, then the possibility of, you can say, less number of water of crystallization can be released in that case. Then we go to deliquescence, another property, deliquescent substances. So deliquescence is, you can say, we can even call them as desiccants. They absorb water out of air, so they keep absorbing water until they become, or they dissolve themselves into it. So these are substances which readily absorbs water out of the air until they dissolve into, or you can say they dissolve to form liquid solutions. So now over here we can say deliquescent, sodium hydroxide is very much deliquescent in nature, potassium hydroxide is there, ammonium chloride is there, calcium chloride is there, then this MgCl2 dot 6 molecules of water. Magnesium chloride is very much deliquescent. Sodium nitrate is deliquescent. Deliquescent in the sense, like, let's talk about this common salt that we eat. So in rainy seasons, most of the time, common salt becomes little, you can say, clumpy. So it absorbs some moisture from the surroundings and it actually dissolves in it. So it becomes, you can say, a lot of lumps are there in the salt. Otherwise, it doesn't have it in the dry form. So again, NaCl is not deliquescent in nature. This MgCl2 is added in the common salt that we eat. That is deliquescent in nature, and that's why it is able to, we are able to see that those, you can say, moisture filled lumps in the salt. So NaCl is never deliquescent. Just remember that it doesn't have the capacity to absorb moisture from the surroundings, from the dry, from the, you can say, humid air. So it cannot form solution. Now if we talk about the sodium hydroxide, the sodium hydroxide we get in the form of pellets in the lab. So white color pellets are there. So if you keep it in the open atmosphere for some time, you will see it will start changing into liquid form, because again that is deliquescent in nature and it can absorb moisture from the surroundings. So immediately we have to weigh it. We have to weigh the pellets of sodium hydroxide and we need to add it in the desired amount of water just to make liquid aqueous sodium hydroxide. Then we go to, so we even call them as one more few more examples we can take. We forgot about the acids. So we can even we can use concentrated H2SO4 or concentrated H3PO4. They actually belong to a category, something we call it as desiccants, right? So then we even have a term hygroscopic substances. Even concentrated H2SO4 and concentrated phosphoric acid, even concentrated NaOH can be used as a can be called as a hygroscopic substance. So hygroscopic. So these are substances that readily attracts water from the surroundings through either absorption or adsorption. So example is ethanol, C2H5OH. We can add concentrated H2SO4 also in this, and we can add concentrated NaOH also in this. Concentrated NaOH is also called as lye, etc. So adsorption is basically what? Adsorption is when any kind of component is just going to stick on the surface. It's not going to get absorbed. It is not going to penetrate the layer. It's going to stick to the surface. Now the surface, you can say whether they are sticking the surface in the form of some physical attraction, some chemical attraction, some chemical reaction, that is a very different topic that mostly we teach in surface chemistry. So adsorption is just sticking on the surface, with some bonds involved. It can be some just loose bonding, it can be just physical attraction. So some loose bonding can be there, or it can be a strong bonding with the help of chemical bonds over there. Both are possible. That's why we call this adsorption as physisorption, physical adsorption and chemical adsorption also. So absorption is a normal process, just like you have a cloth and you put it in water, it absorbs water, so the water penetrates entire fabric over there. So adsorption is like it stays on the surface. Then we go to the last type of substances, dehydrating substances, or dehydrating agents also we can say. Now whenever we get DE in the starting, most of the time in chemistry, DE stand for removal. So hydration is addition of water. Dehydrating means you're removing water. So substances that dries or removes water from any material, right? So it may be a chemical compound, so which can be used to drive a dehydration reaction. So it can absorb moisture from the surroundings also. So we can say, so its major job is to remove water. Substance that dries or removes water from material. It can be a chemical compound, used to drive a dehydration or dehydration reaction. So example again, concentrated H2SO4, we can use alumina. Alumina is nothing but aluminium oxide, Al2O3, right? So we can use one reaction. So let's say we have our ethanol, C2H5OH. So concentrated sulfuric acid is our dehydrating agent. And it's giving us ethene, C2H4, and water is removed. So dehydration, like removal of water, that's why we call it as dehydration of ethanol. So now in this, let's open the structure. This is ethanol. OH group is attached. All bonds over here are covalent bonds. So again, we are not discussing any kind of detailed mechanism over here, just you can say basic reactions of what is happening over here. So when we open the structure, this is our ethanol. We even call it as ethyl alcohol. So when you open the structure into this, these are all covalent bonds. These are all covalent bonds over here, right? So can you see this OH and this hydrogen? So if we pick it up, like we just, if we try to remove it, right? So this carbon always forms four covalent bonds. Carbon atomic number is 6, 2, and 4. So 1, 2, 3, and 4. So obviously these bonds are, if they are going to be cleaved, if they are going to be broken down, so carbon needs to form another bond just to complete its covalency with itself. This is what we even call it as catenation, that we'll be starting in organic chemistry. That is self-linking of carbon atoms with other carbon atoms to form long chains, branches, rings, right? So then what we are going to get? We are going to get ethene. Ethene is carbon with a double covalent bond, and the rest bonds are going to remain intact. And that's what I've written over here. C2H4. This is what we call ethene. It's a gas. So water, this entire water is removed. That's why we call it as dehydration of ethanol. What is driving the reaction over here? Concentrated sulfuric acid. It's a dehydrating agent. Even phosphoric acid can also be. So most of the time we can say dehydrating agents remove water which is which is chemically bound to a substance. Like this is, if you can see this, this is chemically bound to a substance over here. So water of crystallization, right, simply removes excess water present in a substance which is chemically bound to it. Alcohol dehydration, alcohol causes dehydration, right? So even we like too much of alcohol can cause dehydration in the body also, right? So I hope you have understood this chapter. Then in the next video, we'll be discussing about practice questions of this chapter, acid bases salts, and some extra topics also.